Welcome to Unit 4, Lesson 7, Inequivalent Equations. Let's see what happens when we square each side of an equation. Looking at our exponent rules, which may come up in this lesson, but we need them for the unit. Okay, notice and wonder. What do you notice? What do you wonder? Well, there's two ways to solve the first one. Simply take the square root of both sides, and we know that x equals plus and minus 2. Now, if you were looking at the top one strictly as a polynomial, you know that it has to be equal to 0 so that you can factor it. If you do x squared minus 4 equals 0, if you factor this polynomial, you get x plus 2 and x minus 2 equal to 0, which is just like the second one. So when we have a polynomial equal to 0, we set each factor separately equal to 0 and solve. It's called the zero product property. Subtract 2 from both sides. X equals 2 and x equals negative 2. That's the same as what we got if we were just taking the square root on both sides. So these expressions are the same. They just look different. Okay, what are we looking at here? Tyler was solving the equation x squared minus 1 equals 3. Then he said some words, and Priya said something back. A, looking at the first one. Figure A is related to x squared minus 1 equals 3. What does this mean? This means that y equals x squared minus 1 and y equals 3. So if you have two separate equations, you put one into y1, one into y2, and this is the graph you'll get. And the solution is the point of intersections between the lines, between the dashed line and the curved graph. For figure B, you have y equals x squared, y1, and y2 is y is equal to 4. The dotted line is 4, and this tells you the intersections between both lines. It changes the graph and the solutions if you add one to both sides, because there are two separate equations that have been set equal to one another, so you can find the points of intersections. And you can tell by looking at the graph they intersect in different points. Other than that, it's not much to this problem. If you look closely at both graphs, they both have the same points of intersection. Well, not the same points. One's at 2, 4 and negative 2, 4, but they have the same roots of 2 and negative 2. The blue points of intersections are negative 2, 3, and positive 2, 3. And figure B is 2, 4 and negative 2, 4. So they got the same roots, but different points of intersection. So the solution, we just look where the lines intersect and find the solutions. For B, for C, the same thing. Use the graphs to explain why the equation had the same solution, and we did that because if you take x squared minus 1 equal to 3, we add 1, we get x squared equal to 4. I probably should have moved it over. And take the square root, you get x equals to 2, plus 2, and minus 2. That's what x is equal to. That's not what y is equal to. So with C, you have x squared equals 4. Take the square root, x is equal to plus and minus 2. So they got the same x value, not the same y value. So looking at this problem, Tyler got one answer. But what Tyler forgot was that when you take the square root of a positive number, you get a positive answer and a negative answer. Okay, Ham was solving an equation. He said, I know that half of x plus 3 is 4, so x plus 3 must be 8. Since 8 is half of 4, this means that x is 5, which is correct. Use Hein's reasoning to solve the equation x plus 3 quantity squared equals 4. Okay, so when we take the square root of both sides, we get x plus 3 is equal to 2, and x plus 3 is equal to negative 2. And if we solve it from here, x could be negative 1 or x could be negative 5. Now, what advice would I give to someone who is going to solve the equation like this? Remember, when you take the square root of a positive number, you get two answers, one positive, one negative. You could always graph it and make sure that your solutions are right. You always want to check the solutions to make sure they work. Okay. May was solving this equation. She squared both sides. Because when you have an equation, you have to look at what's being done to the variable, and you have to do the opposite. What's being done to the variable? Well, it's under a radical, and it's being subtracted by 1. So PEMDAS says do your exponents. There are no parentheses here, but everything under the radical symbol is a group. The entire radicand is a group. So you got to square both sides first, and here's May's work. So May's work is correct. Now, when we get down to 2, Tyler said, I tried your technique to solve, but it didn't work. A square root cannot equal a negative number. So there are no real solutions. We'll learn about this in a couple of lessons. Okay, so let's solve. Just like the previous one, the t is under the radical symbol, so we got to square it to get rid of the radical. So t plus 4 pops out because it's part of a group, equals 9. You subtract 4, and then t equals 5. How do I know this is true? 5 plus 4 is 9. If I stick 5 plus 4 in there, and I take the square root of 9, I get 3. So it works. You can always stick your answers back in to the original equation to make sure your work is correct. Okay, for number 2. Whenever you see a negative next to a term, it's negative 1 times that term. So the first thing I would do would be to divide both sides by negative 1. So you get 10 is equal to the square root of a. We square both sides, and then we get a is equal to 100. All right, for the next one. The 4 is not under the radicand. It's not part of the group. So the first thing we have to do is move the 4. So you get 3 minus w is equal to 4. Now we square both sides. We get 3 minus w is equal to 16. We subtract 3. Negative w is equal to 13. Now, when you solve an equation, you cannot have negative 1 as an exponent. So we're going to have to divide by negative 1 on both sides, and w is equal to negative 13. Okay, again, this 9 is not part of the radical, so move the 9. And then we get the square root of z is equal to negative 9. Now, a square root cannot be equal to a negative right now, so we have no real solutions.